Imagine we have a vertical wall and a floor we call the x-axis. We're going to treat the wall on the left side of the diagram as immovable. This is an approximation because no real wall is immovable, but that's the nature of simplified models. We make assumptions that allow us to draw conclusions without too much math. We can improve the model later if we want. On the floor, we place an object, and it will have a mass m. We will assume there is no friction between the mass and the floor, allowing the mass to move freely in the x direction if a force is applied. We then attach that mass to the wall with a spring. This spring will be assumed to be massless so that we don't have to account for it anywhere in our mathematical equations we'll eventually set up to describe this system. Furthermore, we will assume there is no gravity. Once the spring is attached, the mass may move back and forth, but we can stop it and place the mass at rest in a position where there is no force acting on it. The position of the mass along the x-axis where it experiences no force is labeled x equals 0 and is called the equilibrium position. We can think of the x-coordinate of the mass as the displacement from the equilibrium position. Every system like this has some equilibrium position, usually given the coordinate 0, where the force is 0. Now we are going to take this mass at the equilibrium position and push it toward the wall so that the spring is compressed compared to its normal equilibrium length. When we do this, we will find that the spring exerts a force on the mass in the positive x direction. When we let go of the mass, it will move toward the right under the influence of the force. It will eventually reach the equilibrium position where the force on the mass is 0. The mass will not stop here, however, because it has a velocity in the positive x direction. So it will continue to the right, causing the spring to be stretched compared to its length at equilibrium. And when the spring is stretched like this, it exerts a force on the mass that is in the negative x direction. This force eventually brings the mass to a stop because it opposes the motion to the right. After the mass comes to a stop, the force will make the mass move in the negative x direction. The mass will move toward the left, reaching the equilibrium position and moving through that such that the spring is compressed again. The force to the right will bring the mass to a stop and cause the mass to move back toward the right through the equilibrium position and eventually far enough to stretch the spring again. If we were to measure the magnitude of the force exerted by the spring, we would find that it changes constantly during the motion of the mass, but it is always proportional to the displacement x. We'll talk more about this in a bit. This system is called a harmonic oscillator. It is sometimes called the simple harmonic oscillator to indicate that assumptions have been made to make it, well, simple. The harmonic oscillator is one example of a general class of motion called harmonic motion. All harmonic motion share certain characteristics. In every type of harmonic motion, an object moves under the influence of a force, called the restoring force, that always points in the direction opposite the displacement from equilibrium. The magnitude of the restoring force is always proportional to the object's displacement from its equilibrium position. This means that the force gets larger in magnitude in direct proportion to the object's distance from its equilibrium position, and that it goes down in magnitude as the mass gets closer to its equilibrium position. Because the restoring force goes up as the displacement goes up, every object subject to a force like this will reverse its direction of travel when displaced too much, because eventually the restoring force becomes large enough, with enough displacement from equilibrium, to overcome any motion. This is true for positive displacement from equilibrium as well as negative displacement. Thus, the motion of an object becomes periodic, oscillatory, or harmonic. All of these terms mean about the same thing. During this harmonic motion of the object, the position, velocity, kinetic energy, and potential energy all vary with time. Velocity is large near the equilibrium position and smaller when displacement is large. If the system is conservative such that there are no dissipative forces, kinetic energy and potential energy must always sum to one number, the total energy at the start of the object's motion. Thus, as kinetic energy goes up, potential energy must go down. When kinetic energy goes down, potential energy must go up. In other words, total energy is fixed at the start of the motion. We have looked at harmonic motion of a harmonic oscillator, a system in which the restoring force is provided by a spring. We could have looked at a pendulum instead, where the restoring force is provided by gravity at the expense of a great deal of extra time. We would have reached the same conclusions about harmonic motion. For all harmonic motion, the source of the restoring force does not matter so long as it has the characteristics we have talked about. Any system that possesses a harmonic restoring force will have similar behavior even if they look like very different systems such as the harmonic oscillator and the pendulum. It turns out that a chemical bond provides a restoring force that can be considered mostly harmonic. Because of this, we can model bonds in molecules as though they are springs, and this is very helpful in all sorts of calculations. To emphasize this, we sometimes draw two bonded atoms, such as two nitrogen atoms, with the bond lines replaced with a spring. Atoms aren't really attached by springs, but using that symbol for the bond is shorthand for indicating that the force holding the two atoms together is a harmonic force. This is really the basis for molecular mechanics, a method in computational chemistry for computing the total energy of molecules. The harmonic oscillator model is used extensively when talking about molecular vibrations because vibrations are really just the relative motion of atoms in a molecule subject to a restoring force. We also use the harmonic oscillator model when talking about changes in vibrational energy in vibrational spectroscopy. The restoring force in harmonic motion can also be provided by an electric field, such as that felt by electrons in a molecule. If electrons are exposed to a harmonic restoring force, they will move in an oscillatory fashion, and this can be used as a starting point for thinking about electronic spectroscopy of atoms and molecules. Even though the harmonic oscillator model may initially seem far removed from chemistry, it plays a central role in understanding the behavior of atoms and molecules. And that's an introduction to harmonic motion.